The cold hit different in Montana Territory. One settler learned that his first winter in 1879, when his brand new stovepipe rusted clear through after 3 months, filling his cabin with smoke and forcing emergency repairs in sub-zero cold. He had installed his heating exactly as every frontier manual recommended: bare galvanized metal pipe, standard fittings, trusted by homesteaders from Wyoming to the Dakotas. By spring, he faced an $8 replacement bill, and the same failure would repeat every 2 to 3 winters. Across the territory, settlers were trapped in this costly cycle, with pipes rusting out season after season. This settler quietly applied a traditional coating to his next pipe that neighbors mocked as wasteful paint on something that gets hot. While their stovepipes kept failing every few years, his treated system held strong for 25 years. What did he grasp about protecting metal that every other frontier builder was missing? The Bitterroot Valley stretched wide and unforgiving in the autumn of 1878, when Eric Anderson first spotted the smoke curling wrong from his neighbor's cabin 3 miles downstream. By the time he rode over to check, Thomas Brennan was already hauling water buckets inside, cursing the rust hole that had opened clean through his stovepipe where it curved toward the roof. The acrid smell of wet ash filled the small cabin as Brennan stamped out embers that had scattered across his wooden floor. Brennan had followed the installation guide from the Helena hardware catalog exactly. 18-gauge galvanized sheet metal pipe, standard joints sealed with furnace cement, the whole assembly running straight up through a simple roof collar. The method worked fine back in Ohio, where he'd grown up, but Montana's extreme temperature swings told a different story. During the day, autumn's sun heated the metal hot enough to burn skin. At night, temperatures plunged 40 degrees, causing rapid contraction that cracked the furnace cement and allowed moisture to penetrate the joints. The real killer was condensation. When warm, moist air from cooking and breathing hit the cold upper sections of pipe during sub-zero nights, water droplets formed on the inner walls and pooled at the joints. This trapped moisture, combined with the acidic compounds from burning pine and cottonwood, created the perfect conditions for rapid oxidation. Within 2 winters, pinhole leaks appeared. By the 3rd winter, chunks of rusted metal fell into the firebox. Anderson had watched this pattern destroy pipes throughout the valley. The Kowalski family down near the creek had replaced their system twice in 4 years. Jim Morrison's pipe failed so spectacularly during a February blizzard that his family nearly froze before he could rig a temporary fix. The Jensen brothers, practical men who'd homesteaded from North Dakota, had started budgeting $12 every other year just for stovepipe replacement. The accepted wisdom made sense on paper. Galvanized metal cost $3 per section, installed quickly, and conducted heat efficiently. The territorial building inspector who'd surveyed the valley in 1877 had praised the settlers for choosing modern, standardized heating solutions over the crude stone and clay arrangements used by some immigrant families. But standardized solutions built for milder climates weren't holding up to Montana's punishing weather cycles. Anderson's background set him apart from most valley settlers. His father had been a ship carpenter in Bergen, Norway, where preserving wood and metal against harsh maritime conditions meant the difference between profit and disaster. The elder Anderson had taught his son that any material exposed to moisture and temperature extremes needed protection, whether it was a ship's rigging or a cabin's heating system. When Eric emigrated to Montana Territory in 1876, he brought along his father's recipes for protective coatings made from readily available materials. The coating itself was deceptively simple. 1 part refined linseed oil mixed with finely ground lampblack in a ratio that produced a paint-like consistency. Linseed oil, pressed from flax seeds and available at any general store for 15 cents per pint, polymerized when exposed to air and heat, forming a tough waterproof membrane. Lampblack, the carbon soot scraped from lamp chimneys and oil lamps, served multiple purposes beyond just pigment. The carbon particles absorbed and radiated heat more efficiently than bare metal, while also providing additional protection against oxidation. But applying the coating required precise timing and technique. The pipe had to be completely clean and dry, wiped down with kerosene to remove any traces of manufacturing oils. The coating went on in 2 thin layers, with the first layer cured at low heat for 6 hours before the second application. Most critically, the coating had to cure slowly over several days at gradually increasing temperatures, allowing the linseed oil to fully polymerize without bubbling or cracking. When Anderson first mentioned his coating method to other settlers during a barn raising that October, the response was immediate and unanimous. Waste. Thomas Brennan shook his head and muttered about painting something that gets hot enough to cook on. Morrison called it fancy European nonsense and suggested Anderson was overthinking a simple problem. Even Hans Miller, the German mason who'd built some of the finest chimneys in the territory, seemed skeptical that any coating could withstand the intense heat cycles of a working stovepipe. The skepticism ran deeper than mere practicality. These settlers had come west to escape the old world's complicated solutions and embrace American directness. Spending time and money on protective coatings felt like the kind of excessive preparation that kept men poor and dependent. Real frontiersmen, the thinking went, accepted that things wore out and simply replaced them when they failed. Anderson's methodical approach to material preservation struck many as unmanly hesitation in the face of straightforward problems. The social dynamic shifted further when word spread about Anderson's other modifications. He'd raised his cabin's foundation 6 inches higher than standard plans recommended, claiming it would prevent moisture wicking up from the ground. His roof extended 18 inches past the walls on all sides, throwing rainwater and snowmelt well away from the foundation logs. Neighbors began referring to his cabin as the place with the big hat, and not kindly. By November, when the first serious cold snap hit the valley, the divide was clear. Most settlers had installed their heating systems according to standard practice: bare metal pipes, minimal foundation protection, standard roof lines that channeled water directly onto the ground beside their walls. Anderson had quietly applied his father's preservation methods, creating a heating system that looked identical from the outside, but incorporated generations of maritime knowledge about protecting materials from moisture and temperature extremes. The approaching winter of 1878 would test both approaches against Montana's legendary severity. The winter of 1878 came early and stayed late, with the first hard freeze locking the Bitterroot Valley in ice by mid-November. By December, temperatures regularly dropped 20 below zero, and Anderson's coated stovepipe began revealing advantages that went far beyond simple rust prevention. The lampblack in his coating was absorbing solar radiation during the brief daylight hours and continuing to radiate that stored heat well into the evening, extending the thermal efficiency of his entire heating system. This secondary benefit emerged from a principle Anderson had learned not from his father, but from a Salish elder named Red Fox, who traded furs at the Hamilton settlement. Red Fox had observed how certain stones near his lodge stayed warm long after sunset, while others cooled immediately. The elder had explained that dark surfaces captured and held heat energy differently than light ones, a knowledge his people had used for generations when selecting stones for cooking fires and warming beds. When Anderson mentioned his lampblack coating, Red Fox nodded knowingly and suggested the settler was inadvertently creating what his people called heat-keeper surfaces. The science proved itself through January's brutal cold snaps. While neighbors burned cord after cord of split pine trying to maintain cabin temperatures above freezing, Anderson's system required 30% less wood for the same heat output. His coated pipe was functioning as both a rust barrier and a thermal mass, storing heat during peak burning periods and releasing it gradually as the fire died down. The carbon particles were acting like thousands of tiny heat sinks, each one absorbing infrared radiation and re-emitting it slowly. Temperature measurements taken with a simple mercury thermometer revealed the full scope of the advantage. At 3 feet from Anderson's stove, the air temperature held steady at 68 degrees even 2 hours after banking the fire for the night. In Thomas Brennan's cabin, equipped with a standard bare pipe, the same measurement dropped to 45 degrees in the same time frame. The difference wasn't just comfort, it was survival margin during the valley's harshest weather. But Anderson had also applied his preservation philosophy beyond the stovepipe itself. He discovered that the intense heat cycling was causing his chimney collar, the metal sleeve that sealed the pipe's passage through the roof, to expand and contract enough to crack the surrounding mortar. Rather than accept this as inevitable maintenance, he'd wrap the collar with strips of canvas soaked in pine pitch, creating a flexible seal that moved with the metal's expansion while maintaining weatherproof integrity. This technique came from his conversations with Wolfgang Richter, a Bavarian immigrant who'd worked as a chimney sweep in Munich before homesteading near Stevensville. Richter understood that European masonry techniques, developed for mild climates, failed catastrophically in Montana's extreme temperature swings. He'd taught Anderson that successful preservation required accepting movement rather than fighting it, using flexible materials that could accommodate thermal expansion without breaking the protective barrier. The pitch and canvas collar seal proved its worth during a January thaw that sent temperatures swinging from 10 below zero to 40 above in 18 hours. Brennan's rigid mortar seal cracked completely, allowing melting snow to pour directly onto his cabin's interior walls. Morrison's collar failed so dramatically that chunks of mortar fell into his firebox, nearly extinguishing his fire during the coldest night of the winter. Anderson's flexible seal expanded and contracted smoothly, maintaining perfect weatherproof integrity throughout the temperature swing. By February, the preservation advantages had compounded beyond simple material protection. Anderson's efficient heat retention meant he was cutting firewood once every 10 days instead of daily, freeing up hours for other survival tasks. His sealed collar prevented ice dams from forming, where melting snow refroze around the chimney opening, eliminating a dangerous leak source that plagued most valley cabins. The stable heating system also kept his food stores from freezing, preventing the spoilage that had already cost several neighbors significant portions of their winter provisions. The contrast became impossible to ignore when March storms tested every cabin's heating system with wet, heavy snow, followed by rapid melting. Brennan's uncoated pipe had developed 3 separate rust holes, forcing him to pack them with furnace cement that cracked out within days. The Kowalski family was burning green cottonwood because they'd exhausted their seasoned wood supply trying to compensate for their inefficient heating. Jim Morrison had already ordered replacement pipe sections from Helena, resigned to complete system failure before spring. Anderson's coated system showed no signs of deterioration. The carbon-enriched surface had actually developed a deeper, more uniform black finish, as months of heat cycling had fully cured the linseed oil coating. More significantly, his chimney collar remained perfectly sealed, while his efficient heat retention had left him with enough seasoned firewood to last well into April. The preservation techniques weren't just preventing failure, they were creating a margin of safety that could mean the difference between surviving a harsh winter and facing potentially fatal shortages. The most revealing test came during the March 15th blizzard that dumped 4 feet of snow across the valley in 36 hours. Families with failing heating systems faced impossible choices between burning unseasoned wood that produced dangerous amounts of creosote or rationing fuel and risking hypothermia. Anderson's efficient system allowed him to maintain full heat throughout the storm while actually reducing his wood consumption, as the thermal mass effect of his coated pipe required less frequent stoking to maintain consistent temperatures. When the storm cleared and neighbors emerged to assess damage, the evidence was undeniable. Standard heating systems had suffered multiple failures, required emergency repairs, and consumed wood supplies at unsustainable rates. Anderson's preservation approach had not only prevented failure, but had transformed his heating system into a more efficient, more reliable source of survival heat. The question facing every settler in the valley was whether traditional thinking about material replacement would prove more costly than investing in proper preservation techniques. Spring brought new challenges that standard construction methods couldn't handle. When the April snow melt began, Anderson watched water cascade off every roof in the valley, but the real damage came from where that water went next. Most settlers had built their cabins with simple board and batten siding that met the foundation logs directly, creating a perfect pathway for moisture to wick up into the wood structure. Within weeks of the thaw, dark stains appeared on cabin walls throughout the valley as rot began its inevitable work. Anderson had learned about moisture barriers from Klaus Zimmermann, a German carpenter who'd homesteaded near Derby after working on grain elevators in Hamburg. Zimmermann understood that European building techniques had evolved over centuries to deal with persistent dampness, unlike American frontier methods that assumed dry conditions most of the year. The German had shown Anderson how to create a capillary break using thin sheets of birch bark positioned between his foundation logs and the first course of siding boards. The technique required precise installation. Zimmermann had taught Anderson to harvest bark in long strips during late spring when the sap was rising, making the material pliable and less likely to crack. The bark had to be dried slowly in shade for 6 weeks until it reached the consistency of thick leather, then cut into strips exactly 4 inches wide. These strips were laid over the top of each foundation log with a 1/2-inch overhang on both sides, creating a barrier that prevented ground moisture from climbing into the wall structure while allowing any trapped moisture to drain outward. But Anderson had taken the preservation concept further than Zimmermann had suggested. After watching how effectively his linseed oil coating protected the stovepipe, he'd begun treating other metal components throughout his homestead with the same mixture. His roof flashing the thin metal strips that sealed joints where the chimney met the roof line received the same careful coating process that had protected his stovepipe through the winter. The flashing application required different techniques than pipe coating. The metal had to be heated with a small flame until it was warm to the touch, but not hot enough to cause the linseed oil to smoke. Anderson applied the coating with a piece of sheepskin wrapped around a stick, working quickly to achieve even coverage before the metal cooled. The process took 3 separate applications over 2 weeks, with each layer cured at ambient temperature rather than the accelerated heat curing he'd used on the stovepipe. By summer, the preservation advantages had extended to his livestock buildings. Anderson's barn doors, treated with the linseed oil mixture, showed no signs of the checking and splitting that had already opened gaps in his neighbors' untreated wooden doors. The coating had penetrated deep into the wood grain, creating a barrier against the daily expansion and contraction caused by Montana's extreme temperature swings between day and night. The door treatment had come from conversations with Magnus Eriksson, a Norwegian immigrant who'd built ships in Stavanger before settling near Hamilton. Eriksson had explained that ship timber required protection against both water penetration and the constant stress of thermal movement. Wood that wasn't properly sealed would develop stress cracks within 2 seasons of exposure to maritime conditions, and Montana's climate created similar challenges on land. Erickson had taught Anderson to thin the linseed oil mixture with turpentine in a 3-to-1 ratio for wood applications, allowing deeper penetration into the grain structure. The thinned mixture required 4 coats applied 12 hours apart, with light sanding between the second and third applications to remove raised wood fibers. The final coat included lampblack for UV protection, as Erickson had observed that untreated wood exposed to high-altitude sunlight degraded faster than wood at sea level. The most ambitious application came when Anderson decided to treat his cabin's corner joints with a modified version of his preservation system. Traditional log construction relied on tight-fitting joints that would supposedly seal themselves as the logs dried and settled, but Anderson had watched several neighbors deal with gaps that opened as their green logs seasoned unevenly. Instead of accepting inevitable chinking repairs, he developed a preventive sealing system using pine pitch mixed with finely chopped oakum. This technique combined knowledge from both Zimmerman and Red Fox. The German had shown him how European timber framers used oakum, loose hemp fibers picked from old rope, to seal joints that needed to accommodate movement. Red Fox had taught him that pine pitch, when heated and mixed with plant fibers, created a flexible seal that remained workable in cold weather while hardening enough in summer heat to repel insects and moisture. Anderson prepared the sealing compound by heating pine pitch in a small iron pot until it reached the consistency of thick syrup, then stirring in oakum until the mixture held together when cooled. The compound had to be applied warm, using a wooden paddle to press it deep into the log joints. As the material cooled, it formed a flexible gasket that could compress and expand with the log's seasonal movement while maintaining an airtight seal. The comprehensive preservation approach had transformed his entire homestead into a system designed for longevity rather than replacement. By August, visitors could see the difference immediately. Anderson's buildings showed no signs of the weathering, cracking, and gap formation that characterized most frontier construction after a single year of exposure. His metal components remained corrosion-free, his wood surfaces showed no checking or splitting, and his structural joints had maintained their integrity through the extreme temperature cycles that had already damaged standard construction throughout the valley. The economic implications were becoming impossible to ignore. Thomas Brennan had already spent $14 on replacement materials for his cabin's weather damage, not counting the labor time lost to repairs. The Kowalski family was facing complete re-chinking of their log walls before the next winter, a job that would consume weeks of precious preparation time. Jim Morrison's barn doors had warped so severely that they no longer closed properly, forcing him to consider complete replacement. Anderson's preservation investment had cost less than $3 in materials and required only careful application of traditional techniques his immigrant neighbors had brought from the old country. The difference lay not in expensive solutions, but in understanding that preventing deterioration was always more efficient than accepting replacement as inevitable. As autumn approached and settlers began preparing for another harsh winter, the question facing every homesteader was whether they could afford to keep rebuilding the same failing systems, or whether traditional preservation methods offered a more sustainable path forward. By autumn of 1879, Anderson had begun applying preservation principles to his farming tools, an innovation that emerged from watching his neighbors sharpen their metal implements weekly while his scythe blade held its edge for months. The difference lay in a surface treatment he'd learned from a Blackfoot trader named Walking Bear, who demonstrated how his people preserved iron trade goods using a mixture of bear grease and crushed charcoal, applied while the metal was still warm from the forge. Walking Bear had explained that metal tools worked better when their surfaces were sealed against moisture that caused microscopic rust particles to form along the cutting edge. These invisible pits dulled blades faster than actual use, forcing constant resharpening that eventually wore away so much metal that replacement became necessary. The Blackfoot method created a protective layer that prevented this surface corrosion while maintaining the blade's sharpness through entire seasons of heavy use. Anderson adapted the technique using readily available materials, substituting rendered pig fat for bear grease and mixing it with lampblack from his stove coating supplies. He heated his tools over coals until they were too hot to touch, then rubbed the mixture onto the metal surfaces using a leather pad. The fat penetrated microscopic pores in the iron, while the carbon particles filled surface irregularities, creating a smooth, protected cutting edge that shed moisture and plant sap instead of allowing them to cause corrosion. The tool preservation system proved its value during grain harvest. Anderson's scythe cut clean through thick prairie grass for 6 hours without requiring sharpening, while Thomas Brennan stopped every 30 minutes to hone his untreated blade. By the end of harvest season, Brennan had worn his scythe down to the point where the blade was too narrow to cut effectively, forcing him to order a replacement from Helena at a cost of $4 plus shipping. Anderson's preserved blade remained sharp and full width, ready for another season's use. The preservation philosophy had also transformed his approach to winter fuel preparation. Instead of cutting firewood in autumn and stacking it green like most settlers, Anderson had begun seasoning his wood using techniques learned from Finnish immigrants in the Missoula area. Aro Virtanen, a logger from Karelia, had taught him that properly dried wood burned with 30% more heat output than green wood, while producing significantly less creosote buildup in chimney systems. Virtanen's method required cutting firewood in early spring when the sap was rising, then stacking it in carefully constructed ricks that allowed maximum air circulation while protecting the wood from direct rainfall. The key innovation was creating raised platforms using small logs laid perpendicular to the main stack, lifting the firewood 6 inches off the ground to prevent moisture wicking up from the soil. Each rick was then covered with sheets of birch bark that shed rain while allowing air movement through the sides. The seasoning process took 18 months, but the results justified the long planning horizon. Anderson's properly dried wood ignited instantly, burned clean and hot, and left minimal ash residue. More importantly, the efficient combustion meant he needed 40% less wood volume to generate the same heat output as green wood, reducing both cutting labor and storage space requirements. The clean-burning, seasoned wood also eliminated the creosote deposits that forced most settlers to clean their chimneys twice each winter or risk dangerous fires. Cost calculations had become impossible to ignore by the winter of 1880. Anderson's preservation investments had cost him approximately $7 in materials and required careful timing and application techniques, but had eliminated replacement costs that were devastating his neighbors' budgets. The Jensen brothers had spent $28 replacing stovepipe, tools, and building materials damaged by weather and corrosion. Morrison's maintenance costs had exceeded $35, not counting his labor time for emergency repairs during the coldest weather. The preservation approach had created compound savings that extended far beyond simple material costs. Anderson's efficient heating system required less woodcutting time, allowing him to spend those hours on other productive activities like trapline maintenance that brought in additional income. His tools remained sharp and effective throughout each season, enabling him to complete farming tasks faster and with less physical effort. His weather-sealed buildings required no emergency repairs during storms, eliminating dangerous exposure during the worst weather. The most significant economic advantage emerged from what Virtanen called the cascade effect of proper material preservation. Each prevented failure eliminated the disruption costs associated with emergency repairs, replacement delays, and lost productivity during critical seasons. When Brennan's stovepipe failed during a December blizzard, He lost 3 days of trapline work while making repairs in sub-zero conditions. When the Kowalski family's barn door warped beyond use, they lost 2 days relocating livestock to temporary shelter and another day installing a replacement. Anderson's systematic preservation had eliminated these cascade failures, creating a homestead that functioned reliably through Montana's extreme conditions. His preserved systems worked as intended during critical periods, allowing him to maintain productive routines instead of constantly reacting to equipment failures. The time savings alone had become substantial enough to affect his overall economic survival, as frontier life offered little margin for lost productivity during short growing and trapping seasons. The preservation methods had also begun attracting attention from territorial officials. When the county assessor visited in September of 1880, he noted that Anderson's buildings and equipment showed markedly less depreciation than comparable homesteads, potentially affecting property valuations for tax purposes. The assessor had remarked that most frontier properties lost 40% of their value within 5 years due to weather damage and poor maintenance, while Anderson's careful preservation made his homestead appear newer and more valuable than its actual age. As winter approached again, the economic evidence had become overwhelming. Standard frontier practice of accepting regular replacement costs was proving unsustainable for families operating on subsistence budgets with limited access to manufactured goods. Anderson's preservation approach required initial investments of time and materials, but created systems that maintained their value and functionality over multiple seasons. The question facing every settler was whether they could afford to continue absorbing replacement costs, or whether traditional preservation methods offered the only viable path to long-term economic survival on the frontier. The winter of 1882 arrived with a vengeance that settlers would remember for decades. The first blizzard struck in early November, bringing temperatures that plunged to 38 degrees below zero and stayed there for 6 consecutive days. By January, the Bitterroot Valley was locked under 4 feet of snow, with drifts reaching the eaves of most cabins. This was the winter that would separate working preservation systems from mere hopeful repairs. Anderson's integrated preservation approach revealed a principle he hadn't fully understood when he'd begun applying individual techniques. Preserved systems supported each other in ways that created resilience far beyond the sum of their parts. His coated stovepipes' efficient heat retention reduced the thermal stress on his sealed chimney collar, while his moisture barriers prevented foundation settling that could have misaligned his heating system. The seasoned firewood burned so cleanly that his preserved chimney required no midwinter cleaning, eliminating the dangerous roof work that had already injured 2 neighbors. This system integration principle became critical when January temperatures held below zero for 18 straight days. Standard heating systems began cascading failures as one component's breakdown stressed others beyond their limits. When Morrison's uncoated stovepipe developed rust holes, the reduced draft caused incomplete combustion that rapidly clogged his chimney with creosote. The cleaning attempt in sub-zero conditions cracked his chimney collar, allowing melting snow to damage his interior walls and freeze his water stores solid. The Jensen brothers faced similar cascade failures when their untreated stovepipe joint separated during thermal contraction, filling their cabin with smoke and forcing them to extinguish their fire during the coldest night of January. Without heat, their water barrel froze and burst, their food stores began freezing, and they nearly suffered frostbite while making emergency repairs with numb fingers and inadequate light. The failure of one unpreserved component had triggered a survival crisis that threatened their lives. Anderson's preserved systems handled the extreme conditions without requiring emergency intervention. His coated stovepipe maintained perfect integrity throughout the temperature swings. His flexible collar seals accommodated thermal movement without cracking, and his efficient combustion system prevented the creosote buildup that was choking neighbors' chimneys. Most significantly, his reduced wood consumption left him with adequate fuel reserves when other families were burning furniture and fence posts to survive the extended cold snap. The preservation advantages extended to food storage, where Anderson had applied techniques learned from Norwegian fish preservation methods. He'd constructed a root cellar with double walls separated by sawdust insulation, then sealed the interior walls with a lime-based plaster that prevented moisture condensation. The stable temperature and humidity levels kept his root vegetables, dried meat, and preserved foods in perfect condition throughout the harsh winter, while neighbors dealt with frozen, spoiled, or contaminated food supplies. When the February thaw finally arrived, the damage assessment revealed the full scope of preservation versus replacement costs. The Kowalski family had lost their entire stovepipe system and faced rebuilding costs of $18 plus weeks of labor. Brennan's multiple system failures had cost him $23 in materials and nearly resulted in losing his cabin to a chimney fire. Morrison's cascade failures had damaged not just his heating system, but his interior walls, water storage, and food supplies, creating repair costs exceeding $40. Anderson's heating system showed no signs of deterioration after the brutal winter. His coated stovepipe remained corrosion-free, his collar seals held perfectly, and his chimney drew as efficiently as when first installed. The preservation investment that had cost less than $8 in materials had eliminated what would have been $30 to $50 in replacement and repair costs for a single winter's damage. Word of Anderson's success began spreading through informal networks that spring. When Klaus Zimmermann visited neighboring valleys for carpentry work, he carried detailed knowledge of the preservation techniques that had kept one homestead functioning while others suffered costly failures. Magnus Eriksson shared the wood treatment methods with other Norwegian immigrants settling near the Idaho border, adapting the linseed oil techniques for different climate conditions. The adoption process accelerated when Samuel Crawford, who operated the general store in Stevensville, began stocking linseed oil and lampblack specifically for stovepipe preservation after multiple customers requested the materials. Crawford had witnessed the winter damage throughout the valley and understood that settlers needed access to preservation supplies rather than just replacement parts. By autumn of 1883, the store was selling preservation materials faster than replacement stovepipes, indicating a fundamental shift in how settlers approach system maintenance. The most convincing evidence came from direct comparison. Hans Müller, the German mason who'd initially dismissed preservation techniques as unnecessary complication, applied Anderson's coating method to his own stovepipe after watching his previous system fail for the third time in 5 years. Muller's coated pipe performed flawlessly through the winter of 1883, convincing him that proper preservation was essential craftsmanship rather than wasteful luxury. The techniques spread beyond individual adoption to become accepted community practice. By 1885, new settlers arriving in the valley were receiving preservation instruction as part of standard homesteading guidance from established residents. The territorial building inspector noted in his 1886 report that stovepipe failures had decreased by 70% in areas where preservation techniques were commonly used, significantly reducing winter emergency calls and property damage claims. 23 years later, when Anderson finally replaced his original stovepipe in 1903, the coated system had outlasted 6 complete generations of standard pipes installed by his neighbors. The preserved pipe showed minimal corrosion and could have continued functioning, but Anderson upgraded to accommodate a larger heating system for his expanded homestead. The old pipe, still in serviceable condition, was installed in his workshop where it functioned effectively for another decade. Modern building codes reflect lessons learned from frontier preservation experience. Current standards require corrosion-resistant coatings on heating system components, moisture barriers between foundations and wood structures, and proper seasoning for structural timber. The principles that kept one Montana settler's systems functioning for decades have become foundational requirements for durable construction, proving that traditional preservation knowledge offers more reliable solutions than accepting regular replacement as inevitable maintenance cost.